Unit 4, Quantum and Reality, Independent, Empirical, and Veiled. Section 1, Quantum Characteristics. The theory of quantum mechanics is the result of our scientific efforts to observe reality at the extreme micro level of subatomic phenomena. In the process, it has generated a plethora of counterintuitive concepts. An Oxford physicist, Ian Atchison, has characterized quantum as a physics of lumps and jumps, as Zainad Zohar explains. The lumps appeared in the early days of quantum theory when Max Planck proved that all energy is radiated in individual packets called quanta, rather than in flowing streams over a continuous spectrum. The jumps appeared a few years later when Niels Bohr demonstrated that electrons jump from one energy state to another in discontinuous quantum leaps. The size of the leap depending on how many quanta of energy they have absorbed or given off. Unlike the concepts of classical physics, the quantum world of lumps and jumps does not fit into our common sense worldview of everyday folk physics. Hodgson suggests that in trying to come to terms with the implications of quantum physics for the nature of matter and of reality generally, it is necessary to look at two broad alternatives. One of them accepts that there is an objective solution to the measurement problem of quantum mechanics. The other doesn't. And therefore, Hodgson suggests accept something like the Neo-Copenhagen approach of de Spagna or the measurement by consciousness approach. De Spagna himself says, phenomena, as we have seen, include an important component contributed by human beings, in the sense that it is our perceptual and intellectual faculties which in large measure demarcate these phenomena within the body of the real. Hodgson notes that even the objective view has two profound implications for the nature of matter and of reality, namely indeterminism and a non-material view of matter, following from the indeterminacy and non-locality of the quantum world. On the first of these, indeterminism, he says, consideration of quantum physics confirms that there is genuine indeterminism in quantum systems. Physical measurements, physical events, and physical laws can at best give probabilities for individual micro events, and while that does not necessarily involve indeterminism for macro events, it can do so. As to the second, the non-materiality of matter, Hodgson says, quantum mechanics does not deny reality to the macro objects and macro events of our experience, but that it does suggest that in certain respects their fundamental nature is not what we assume it to be. Trying to reconcile the quantum mechanical view of macro objects with our common sense view of such objects creates a major problem for those who want to come to terms with quantum mechanics. The description the quantum theory gives of the macro objects in our everyday world does not deny their existence or reality, but it does differ from our common sense views. According to the quantum view, what we call a macro object or a thing is constituted of, to a very good approximation, a multi-particle system. This system could, in principle, be represented by a single, very complicated state function. Hodgson comments, I say to a very good approximation because macro objects are continually interacting with their environment. And so on. On a strict quantum theoretical view, should be represented by a state function for the object plus the relevant environment. And according to standard quantum theory, a state function connects with actual observations only by giving the possibilities and probabilities of the values of various observables if measurements should be made. Given this strange and almost incomprehensible world, which quantum physics insists is the reality of things at the atomic level, how can we explain the fact that it is not the world we see at the macro level of everyday objects? Hodgson attempts to explain this. A macro object may be considered quantum mechanically as a many-particle system with strong mutual interactions among the subsystems of which it is composed. The numbers of subsystems and the strength of their mutual interactions involve significant correlations, such that one, in interactions between the system comprising the macro object and other systems, macroscopically sharp values of macro observables can be manifested, and two, such values exhibit the substantial permanency and consistency of behavior characteristic of a macro object. Hodgson goes on to say that macro observables of macroscopically sharp position, motion, shape, color, etc. would generally be established by the state function with practical certainty. In the case of states involving millions upon millions of particles, the standard deviations around the expectation values for such macro observables would be, for the most part, so small that sharpness by macro standards was not prejudiced. This can, I think, be summarized by saying that although macro objects are indeed composed of millions upon millions of particles behaving according to the bizarre rules of quantum mechanics, because of the huge numbers involved, the probabilities cancel each other out, leaving us with the stable, predictable objects of everyday life.